All right, so today we start with mass-volume relationships. Mass volume, what is the name of mass divided by volume? Density, yeah? So we talk about density today. Do you think the density of the soil is something constant or changing in time? Changing in time. But that is the density of the whole soil, the bulk density of the soil. The density of the individual particles on the soil, they tend to be more or less constant. Yeah? The density of individual particles, think about the density of a rock, it's just a big fragment that will be relatively constant over time. Even if you fragment that rock in small pieces, the density of that individual particles will be similar to the density of the original rock. Now, the density of the soil overall, including pore spaces, that is variable. And this is why we are interested, Salam. That is why we are interested in studying and understanding density, because some of the things that are related to the soil use will be related to density. The compaction of the soils will be related to density. So, density being, as you all know, mass over volume, you will have in the soil the mass of the solids, we have the mass of the water, and we have the mass of the air in the soil. What is the mass of the air? What is the mass of the air in the soil? How much do you consider the mass of the air?
40.
0, yeah? 0. So the mass of the air, if you have a balance here, it's just normal atmospheric pressures, the balance will mark 0 for you. So the balance will mark the weight. Yeah, the weight is the mass times the acceleration of gravity. The force that any mass exerts over another object by its mass, by gravity, is the multiplication of the mass of the object times the acceleration of gravity. So we should refer to mass, not as weight. In general, it's more appropriate for us to talk about mass than talk about weight. So for example, always informally we are saying this is a heavier soil than the other one. This soil is heavier than the other one. What we mean is this soil has more weight per volume, yeah, but that weight is not even the correct way of saying it. The soil has more mass over volume, okay? The weight is the force, but we are always referring to mass when we talk about weight. So the more technical language is always talking about mass than talking about weight, or talking about some things heavier or lighter, yeah? The volumes we will have also, the volume will be the same. The volume of the solids, the volume of the liquids, and the volume of the air. The volume of the air and water in the soil will be the volume of the pores. Yeah, you have the volume of the solids and you have the volume of the pores. This volume of the pores is what is flexible in a soil. When you compact the soil, what you're actually doing is you are removing the volume of the pores. The volume of the particles is just concentrated in a smaller volume, yeah? And the volume of the pores are disappearing. What you're actually doing when you compact the soil, you're making this volume of water and air here smaller, okay? So the soil compaction can happen, for example, if you use a tractor to harvest or doing something. The weight of the tractor is pressing down the soil, and then you promote this compaction of the soil. So to understand if the soil is more compacted or more light, let's say, or less dense, more fluffy in a way, we measure this property which is called bulk density, yeah, which is only the mass of the solids over the total volume. Why we do not consider, yeah, the volume of the liquids when we measure the density? Because the volume of the liquids is variable. So we always have to take in account that when we measure density, we are talking about the mass of the particles. Never we are taking into consideration the mass of the liquids, because depending on the moisture, this will be more or less. Yeah. So we want to have something that reflects a property of the soil, not a state of the soil in that moment. We want to have some property that is reflecting how the soil is, not the moisture content that the soil has at that moment. So we exclude the weight of the water whenever we are doing mass volume relationships. It's always we use the mass of the solids. Okay. So we were talking before that we have two types of densities in the soil. One is called the particle density, and we have the bulk density. The particle density is the density of the particles without considering the pore volume. Imagine if you have a block of rock, the density of the rock will be the density of a fragment of that rock. It's not about the pore space, it's about the density of the mineral in itself. And that will not vary too much for the minerals in the soil, will be between 2.6 and 2.75. As a good guess, you can say 2.65 always. We very rarely need to measure particle density. The density of the particles in the soil, very rarely we need to measure that. Yeah? It's important to mention also that if you have high organic matter in the soil, then the organic matter is part of the solids also in the soil, and that organic matter will have a very much lower particle density, even below 1, yeah, 0.6, 0.8. The particle density of organic matter will be sometimes very low, and that can mess up if you make any calculations only by the assumption that the density of the solid, the particle density is 2.65, but if you have high organic matter, then it will average that lower. So you may have a problem with the calculations. But in Oman you have usually low organic matter, so it's a safe assumption that you can just work with 2.65 grams per cubic centimeter. Yeah, grams per cubic centimeter. So also about units, mass over volume, grams per cubic centimeter. 1 cubic centimeter is 1 ml. Yeah, 1 ml is 1,000th of a liter. Okay, if you go for megagrams, is a ton. 1 ton per cubic meter, it will be exactly the same number as 1 gram per cubic centimeter. It's a direct conversion. It's just this. Sometimes you will see in literature tons per cubic meter and megagrams per cubic meter, or sometimes you will see grams per cubic centimeter. That will be exactly the same proportion. 2.65, assume, for the purposes of this course, assume the particle density being 2.65. We will not deal with quantification of particle density in the lab, or it's not something that will change too much the purpose of the applications of your soil by understanding particle density on your soil. If you want to know organic matter content and you think organic matter content is affecting particle density, so you just measure organic matter content instead of measuring particle density and trying to infer organic matter from that. Okay, so normally for mineral particles, particle density always 2.65. You can assume that independently of the size, if it's clay, silt and sand, or if you even have rock fragments. Yeah. So the calculation, how you do it on the experimentally for any density, you want to have volume over mass and volume. So the mass is easy. You can take the weight on a balance. You can take the mass on even balance, any balance. Yeah, the higher the precision, the better. But how do you get the volume? The volume, you have to have some volume displacement. So if you have a rock, this is the case of a rock here. If it's just one single particle, you can submerge that and see how much more is the volume increasing after you submerge that particle in the soil. So So you get the mass in a balance, you get the volume displacement here, and then you have mass over volume. That is your calculation. So simple, the calculation of density. If you have a particle, this is the case of a rock, so there's no pores inside. So if you imagine here, what happens if you have a pore, a porous medium like you have soil, an aggregate of soil? The water will come inside, you know. So this will not work for particle density if you have a porous medium. And the problem is with water has a high viscosity. So water will not go inside every pore in the soil immediately. Some pores will still be occupied by air. So if you want to do that, the particle density with soils, what you need to do is not have an aggregate like this, but the fragmented soil, and you want to use something that is not water, like for example ethanol. Ethanol will be have a higher ability to occupy all the micropores in the soil, whereas water will not. Yeah. So you can get volume displacement by using ethanol, but that can only be done provided that the solids are denser than the liquid that you're using. If you're using ethanol, the soil must be denser than that. If you have organic matter that is with a lower density than the liquids, the organic matter will float because the buoyancy by Archimedes' laws, principles, the buoyancy of any object is a product of the weight of the displaced liquid. Yeah. So if you have something that is less dense, it will not be able to displace enough liquid to go inside. Yeah. So it will not sink, it would float. You have too much buoyancy on the object, and therefore it will float on the surface. So if you have organic matter, high organic matter, maybe you have a problem of quantifying the particle density of that organic matter. You need to do it in some environment where you can apply pressure over it like a syringe. Yeah? Instead of using some tube like this, you have to do it inside a syringe. Anyway, that is beyond the point. The estimation is just displaced volume. You divide the mass by the displaced volume and you will get the density. So book density, what do? You need to do the same thing, but you can do here, instead of having a solid particle, you can have an aggregate of the soil, and you can cover that aggregate with paraffin so the water will not go inside. So all the displaced volume here would also include the volume of the pores. If you have that this is a soil aggregate, and you cover this aggregate with paraffin, the water will not go inside the aggregate. So whatever when this aggregate sinks, the volume that is going up is the volume of the pores in the solids, the total volume of the soil, not only the volume of the particles. So what we want to do with book density, we want to divide the mass of the soil by the total volume. The total volume of the soil, not only the volume of the particles, but the volume of the pores also. So the book density will reflect if you have more pores or less pores, if it's more compacted or less compacted. Yeah? So if it's arranged in a way that is very compacted, you get more density. If it's arranged in a way that you have the structure mixed with more macropores, then you have a lower book density. So book density for you will reflect the state of the soil, if it's highly compacted or not. So book density is like 0.6. You find when you have high organic matter, very, very high organic matter, 40, 50%, or very high organic matter, organic soils, or when you have volcanic soils with volcanic ash materials. Sometimes you will get also book densities of 0.6, 0.7, 0.8, allophonic soils with high allophon, immogolite, that will be very fluffy soils, very low density. 1.6 book density is too high. Normally it reflects a soil that will have some problem with aggregation. For example, when you have high sodium in soil, high salinity with sodium, sodicity, that will mess up with the structure of the soil and that will compact. So when you reach those densities of 1.6, it's already because the number of the amount of pores that you have is very, very low. So what do you expect to see on your soils? 1.3, 1.2, 1.4, yeah, 1.1. And the higher it is, the more compacted the soil. The lower the density is, the more pore space you have, the less compaction you have on the soil. So it reflects the porosity, yeah? And we can use it to calculate porosity. So here the difference between, again, about particle density, which is volume of the particle, mass of the particles over volume of the particles. Bulk density, mass of the particles over total volume, including the pores. Yeah? So you can have some simple calculation by dividing one by the other. And here is how do you calculate the total volume? You can do it by any geometry of the vessel that you have to occupy that soil with. So if it's a cylinder, you have the area of the circle multiplied by the height. Yeah, the area of the circle multiplied by the height, you will get the volume of a cylinder. We will have this exercise in a little bit in the further down the class. Yeah. Again, yeah. So bulk density and particle density is the same thing. Just if you have mass of the particles, if it's divided by total volume, then you get bulk density. If it's divided by volume of the particles, you get particle density. For exams and exercises, I will not ask you to calculate particle density. Just assume 2.65 for all exercises. It's a good estimation, yeah? So here in this exercise is giving you 2.66, but just assume for all the exercises that we will make 2.65. In the exam, I will not ask you exercise about particle density, but yes, I will assume that you know particle density to calculate porosity from bulk density. I will show you in a second. So how do we measure bulk density from field samples? You have a core sampler. Yeah? You can take soil cores from the field. How does it go? You will have an auger like this that has a cylinder, and you will hammer that auger in the soil. You will hammer that auger in the soil, and that auger will take up a volume of the soil as it is in the field. Yeah, as it is in the field. So you will have the volume of the sample that you are taking from the field. It's just a cylinder that you hammer in the soil. Inside the cylinder will be soil. Yeah, you know the volume of the cylinder just by geometry. You have the area of the circle times the height. You can take the volume of the cylinder, and you take this sample to the oven, you dry it, and you measure the mass of the soil, the dry soil. So only the mass of the particles. And then you can divide the mass of the particles by the calculated volume of your cylinder. Does that make sense for you? Is it simple enough? You have an auger that contains a cylinder on top, then you hammer that in the soil, then you take that out, you flatten so you only have soil inside the cylinder. Then you know the volume of that cylinder. You just take the sample to the lab, dry your sample in the oven, take the mass of that soil, and then you divide by the volume, you get bulk density. So that is how you do it in the field. This is the most appropriate way of you doing it. There's a lot of measurements in the lab that just consists in get the sieved soil and put it on a cylinder, hit it 10 times down so it settles, and then you can use mass over volume and do it like that. But that arrangement of the sieved soil will not be the same arrangement that you get in the field with the complete structure of the soil. So doing in the lab with sieved soil will not reflect necessarily what is the bulk density in the field. So here is showing, yeah, what is it showing here? If you have this type of structure, a structure like this or a structure like this, yeah, what do you expect about the density happening here? How will it change from here to here? Which one is more dense? Which one is less dense? This one more dense, yeah? Because you can already see, because of the arrangement of the particles, there is less pore space. There's a higher amount of particles for the same volume. There's a higher volume of particles for the same volume of soil, so you will have to also have more mass of solids for the same volume. If you have more mass of solids for the same volume, you get more density. So porosity, bulk density, they are a measure of how compacted your soil is, how much is the pore space you have. Bulk density increasing from left to right, okay? So let's talk about porosity now. So bulk density is inversely proportional to porosity. Porosity is a percentage of volume, okay? Porosity is how much is the percentage of the total volume of your soil which is occupied by pores. If you compact your soil, you have less volume of pores, so there's less percentage of pores in the soil. Normally, in a healthy soil, you would expect porosity around 50%. Yeah, 50%. When porosity goes down, yeah, it means you have more compaction. If porosity goes up, it means your soil is less compacted. So porosity being the volume of the pores over the total volume, and that can be, if you work out the volume of the pores over the total volume, you can come that is, you will arrive in the formula that you can use bulk density and particle density to calculate porosity. 1 minus bulk density over particle density will reflect for you what is the porosity. So if you assume in general that particle density is 2.65 and you measure your bulk density, 1 minus your measured bulk density divided by 2.65 will give you porosity. Immediately, you will know the porosity of your soil. So this is not something that they reflect the same thing. Yeah, bulk density and porosity, they reflect the same thing. Just as different ways of expressing. Bulk density being a mass-volume relationship, and porosity being the percentage of volumes of the soil, the volume of the soil which is occupied by pores. So you can always assume 2.65 for the purposes of this course, yeah, for this. So if you get porosity is like 0.3, it means a highly compacted soil. If you get 0.6, it's a very fluffy and healthy soil. A lot of pores. You usually want more pores in the soil. In general, the higher the porosity, it's a good thing for your soil. The fluffier your soil is, the better. Now, there is a relationship between porosity and texture. Yeah. Before you read this, just what do you expect? If you have more clays, you have more porosity or less porosity? More porosity. That's correct. Many people answer the other way around. Yeah. You have, with more clays, you have more pore spaces. You have better arrangement. The smaller particles, and they have this ability of flocculating and occupying, making pores within each other. Yeah, even though the pores are smaller. When you have more clays and more silt, the size of the pores becomes smaller, so there's more water retention, but the total amount of pores is higher. The total volume of pores or proportion of the volume of pores in the soil is higher. More clays, more silt gives you more porosity. More sand will give you less porosity, more bulk density. Yeah. So one way of seeing this is, if you have one particle of sand here, imagine that is a microaggregate of clays, the same size of a particle of sand. You have a microaggregate of clays. Inside that microaggregate of clays, there is pores. So in the same volume where you do not have any pore here, here you will have pores inside that microaggregate. So by having clay particles and silt particles, the smaller the particle is, the more it will lead for an arrangement where you have more pores in the soil. So macropores are the pores in between aggregates and in between sand particles. Yeah? And micropores will be the ones that are inside those aggregates. This is highly important because macropores leads to a good infiltration rate. Leads for you to, if you are doing irrigation, you have no ponding, the water will infiltrate well in your soil. Having micropores will allow you for having good water retention. The water availability for your plants will be high if you have micropores. So you need a combination of both things. The size of the pore, you need both of them. If you only have micropores, you have good water retention, but the water will not infiltrate very quickly. It will be ponded. If you have a very heavy clay soil, when you apply irrigation, the water will stay on top, will be very slow moving on the soil. And if you have macropores, then they will have good infiltration. If it's only a sandy soil, you have a good amount of macropores, but no water retention. So water will go in quickly, but will not be retained on the soil. So you need a combination of macropores and micropores. It's important also the macropores not only for water infiltration, but also the friability of the soil. What do I mean by that is how easy it is for the soil to be taken by the roots of the plants. You know, it's the penetration of the roots in the soil. It needs to go against the resistance of that soil particles. And how easy for the roots to do this, the more you have macropores, the easier will be for the plants to occupy the soil with roots. If it's very occupied by micropores, it will be harder, yeah, for these plants. Okay, so the chemical process that leads for the formation of these aggregates, the aggregates of clays that you have here in silt, that creates those micropores. The chemical process, the first chemical process is called flocculation. I think you have not had that lab yet, the flocculation lab? No, you will see this on the lab also. So what is the flocculation process? The flocculation process is, if you imagine that your clays, they have charge, your colloids, they have charge, they're all negatively charged, let's say, yeah? And being negatively charged, you expect them to repel each other, no? So it will not form aggregates. But if you have polyvalent cations, meaning cations that have more than one charge, like calcium, magnesium, aluminium, iron, these polyvalent cations, one charge can satisfy one clay, and the other side can satisfy another clay, and therefore can bind those two clays together. So whenever you have a colloidal, suspension, and you add polyvalent cations, you get flocculation. It means those colloids will bind to each other and form bigger aggregates that will behave like bigger particles. This is the process, the initial process of structure formation in the soil. You did that the opposite. When you did texture in the lab, you added a dispersant. Yeah? You add calgon, sodium hexametaphosphate. Sodium is monovalent, has only one plus, yeah, one valence. That one valence of the sodium means that it can hold only for one clay. The sodium will bind to only one clay, but cannot hold two colloids together, okay? Because it only holds only one, the colloids then do not interact with each other, they do not flocculate. So you can retain those colloids in the suspension. When you're doing it for texture, you want to keep the colloids in the suspension so you can measure them. So you add a dispersant agent, and that dispersant agent is based on adding monovalent cations. You can add potassium also and other monovalent cations that will disperse those particles, okay? Disperse those particles. But if you want to flocculate them, and it's what happens naturally in soils, you want to add polyvalent cations. So you will come in the colloidal class. I don't know if this week or the next one. I need to check with Ahmed. You will see this on the lab. How is the flocculation process happening by adding different ions to the soil? Again, an illustration of macropores and micropores. Water retention is pretty much performed by micropores. Water infiltration is pretty much happening on macropores. Yeah. Porosity in microbes, this is highly important. Yeah? If you imagine an aggregate like this, inside this aggregate there is less, not only water movement, but there is oxygen movement, less oxygen movement. So you get more anoxic conditions. The types of microbes that will live here will be probably facultative anaerobes. So you have more abundance of anaerobic communities inside here, whereas on the surface you will have more abundance of the aerobic microbes. The type of microbes by size also, fungi will likely live on macropores. Bacteria will have more opportunity to live on micropores. So the type of microbes that occupy different spaces in the soil is really dependent on the type of pores that you have. And the function these microbes carry is also different. So if you want to have a diversity of functions in the soil, it means, for example, some microbes are able to degrade a pollutant, some of them are able to cycle nutrients, the other ones are able to fix nitrogen, the other one is able to oxidize sulfur, or reduce sulfur. These things, you want a diversity of environments within the soil space. And having a good structure by having both macropores and micropores in your soil, you created a diversity of environments that leads for also a good diversity of microbes. And the diversity of microbes leads for a good diversity of function in your soil. The biochemical processes in the soil are dependent on the diversity of microbes. And the diversity of microbes is dependent on the diversity of environments that you have in your soil. Okay, so in the exam, we will have some easy calculations of bulk density and porosity. And these are the types of calculations that you need to practice before the next exam. So imagine here that you have a soil core that you took from the field in a cylinder, and you have this soil core has a diameter of 4 centimeters and a length of 10 centimeters. The weight of the container is 5 grams, yeah, and the moist soil plus the container 251 grams, yeah. So the dry soil, after going to the oven, 169. So how do you calculate? You need to subtract the weight of the container from this. So you have 169 minus the 5 grams of the container, 164. That's the weight of your soil, your dry soil. And the volume of your cylinder will be the area of the cylinder times the height. Easy as it is. You get the volume, divide one by the other, you get the density of your soil. Next question that I will ask, is this density high, low, yeah, or it's average, no? It's about normal density that you would expect for a man, about 1.2, 1.3. So it's not a highly compacted soil. If it was 1.45, 1.5, 1.6, then it's a highly compacted soil. So over 1.4, I would say already you're having a compaction problem. But 1.3, still in the normal range. Now if you get that very low, like 1.11, already you have a very, very low density. It's meaning you have organic matter in the soil and you have a good amount of macropores. Easy this exercise? So easy, yeah? Now for porosity, just assume particle density as 2.65. 1 minus book density over particle density times 100 to give it as a percentage. Yeah. So 1.3 we got less exercise divided by 2.65. Yeah. So 1 minus this times 100. Even how it is here, yeah. So if you go just forget this 100 here on the side, yeah. 1 minus mean 100%, yeah. And this one will give you the volume of the particles. So 1 minus this will give you the volume of the pores. If it's 0.5 means 50%. If it's 0.6 means 60%. If it's 0.4 means 40%, and so on and so forth. That easy the calculation. You just need to remember that 2.65 is, I would not give you this on the exam, is part of what I want you to remember is 2.65 as a given for particle density. Yeah, assume particle density as 2.65. A soil sample has a weight of 0.7 kilograms and the volume was found to be 3.5 times 10 to the 4 cubic meters. This is just to trick you, yeah? Changing the units just to trick you so you can do a little bit more brain exercise in these things because it's so simple, just mass over volume, yeah? After drying out, the weight was reduced to 0.6 kilograms. Yeah, the particle specific gravity test gave a 2.6 grams per cubic centimeter. This is giving you a different particle density. Yeah? Not 2.65, but already giving you not 2.65, something different. Determine the following: moisture content, book density, wet book density, porosity. Wet book density is not a thing, yeah? In science you will not use it. It's just the book density is from the dry soil. And porosity. Then moisture content, the weight of the wet soil minus the dry soil will give you the weight of the water, yeah? Divide by the dry weight and then you will get the percentage of moisture by mass. This is a percentage of moisture, percentage of the mass of the soil which is occupied by the water. So it gives you your soil has 16.7% of the weight was water. Dry book density, yeah, mass of the dry soil over the volume of the soil. Kilograms per, so you have to convert this. I don't want you to use any other unit that is not the grams per cubic centimeter or megagrams by cubic meter, which is the same thing. Yeah, they represent the same thing. So you can transform this. The mass you can use in grams, and the volume you can use in cubic centimeters, and that's it. So here would be, this is kilograms, will be 1.7. 1.7 is actually, there's something wrong with this exercise, you can see already. This is not real. You will not find 1.7 in the field. It's very, very hard for you to see. So the example already showing that it's not a reality. If you've seen this data before, never you will see 1.7 grams per cubic centimeter in the field. The top you will see like 1.6 normally. Very hard for you to get to this high bulk density. Yeah, this one here I will not ask on the exams because this is not a thing. Yeah, so if you have your slides you can just cross this. I will not ask about this because wet book density is variable. It's dependent on moisture, so it's not reflecting a property of the soil. Alright, the porosity is just 1 minus book density over particle density. Just you have to make sure that book density and particle density are in the same units. If you use one in different unit than the other one, then it will give a different proportion. 1 over book density over particle density. Yeah, so it's already given on the exercise that is 2.6 for this case. So if it's given, take the number I'm giving you. If it's not given, assume 2.65. All right. In this case, it's given 2.6. So dividing 2.6, 1.7 by 2.6 will give you 1 minus that times 100, 34% of pores. This is already showing you that porosity is too low. So the example is not reflecting a real world scenario. So what, having this bulk density very high will give you a very low porosity. So you wouldn't expect the porosity to be below 0.4. You wouldn't expect bulk density above 1.6. Yeah? So this is showing that is an extreme case. If this is reality, maybe is for example, a cementation horizon. It could be a cementation horizon that you have accumulation of silica or carbonates that will completely remove the pores from that horizon. Then you will get some conditions like this, yeah, which the bulk density is so high and the porosity is so low. So this, you see the information you get by knowing what is the normal values, and you measure something. Already you place your soils in that spectrum. Is it normal? Is it high? Is it low? What should I do to fix this? If it's high bulk density, low porosity, then you need to create structure on your soil. If it's the opposite and you're happy, you're fine. If it's very low bulk density, you will not be complaining about that. Yeah? Don't complain about low bulk density. You can complain about high bulk density. No need to compact your soil if your soil has low bulk density. Yeah? Total porosity is affected by texture, aggregation, depth, and cropped soils. Yeah? Depth, why do you expect depth to affect bulk density and porosity? Yeah, there's the weight of the soil. Yeah, the weight of the soil will compact the lower. If your soil has 1.4, let's say, tons per cubic meter, that's 1.4 tons. If you go 1 meter deep, that's 1.4 tons pressing the lower soil. Yeah, so the soil has a weight, and there's a tendency because of that mass that the lower layers of the soil will be naturally more compacted than the top layers. So there is a function of depth and density. Also, you expect to have more organic matter in the top of the soil, and the organic matter will create those structures on the top of the soil. Cropped soils also, so you have a lot of effects of cropping by the movement of tractors, that will also compact those soils. You have the plowing of the soils, which will fluffen up. So you have some effects depending on the season, but also because you're plowing your soils, you are destroying the structure of your soil. The mixing of the soil will break down aggregates. So you tend to form more compacted soils when you have agriculture management. This is the relationship by texture, yeah? Sand, loam, and clay. So if you have more sand on your soil, even mix, or a more heavy soil, you will have these relationships, yeah? Particle density, don't change. Expect it to be similar. Bulk density will change, yeah? Being less bulk density, the more clays you have. Total porosity, low, medium, high. Pore size, you get small pore sizes in clay, large pore sizes in sand, and medium in loam. Unless this is a very aggregated soil. If you have a very good structure in the clay soil, if it's a very good structure, you will also create macropores, and then you will also be able to have large pores. Yeah, it can happen that some clay soils will be very well structured. If you have a high organic matter and high biological activity, you will have a good structure, and you can also create macropores. Permeability, the infiltration rate of water, high in sand, medium, low in clay. Water retention, also low in sand and high in clays. Is just like a resume table from what we were talking about before. That is it for today. Questions?